Electrical currents. Following the usual convention, we consider that the direction of electric current is given by that in which positive charges are moving. Although the current in solids is due to the motion of electrons which move in the opposite direction. The energy released by the chemical reactions occurring in an electrochemical cell is acquired by the ions taking part in the reactions. And we consider that this energy is acquired by positive charges in accumulating on the positive terminal of the battery, that is, the electrochemical cell. Thus, arbitrarily taking the energy of the unit positive charge on the negative terminal as 0, if the energy acquired by the unit positive charge when it moves from the negative terminal of the battery to the positive terminal is epsilon joule, then E is called the electromotive force of the battery, equal to E volt. Thus, E volt of EMF, that is, the electromotive force, corresponds to E joule of energy stored in the electrochemical cell per unit positive charge. When the charges are moving through the chemical materials, they experience some resistance. This resistance is called the internal resistance of the electrochemical cell. Obviously, the charges have to spend a part of the energy received by them from the chemical reactions to overcome this resistance. Thus, when a unit positive charge reaches the positive pole of the battery, it no longer has any energy, E joule, but has a value V, which is less than E joule. This value V is called the terminal voltage or the electrical potential difference between the terminals of the battery. If R is the internal resistance of the electrochemical cell and the current passing through it is I, then V is equal to E minus IR. In a metallic substance, the valence electrons of the constituent atoms do not remain attached to their respective parent atoms, but get detached, leaving the atoms as ions. The ions so formed are arranged at specific locations, forming a geometric pattern known as a crystal lattice. The free electrons move in the space between the ions in a random fashion. In absence of an external electric field, if we consider any cross-section across the conductor, the number of electrons crossing it in all directions are equal. Hence, the net flow of electrons across the cross-section is 0, which means there is zero current. Now, when such a conductor is connected to the terminals of a battery, an electric field is set up in the conductor and the electrons experience a force acting towards the positive terminal of the battery. Under the influence of this force, the electrons acquire a drift towards the positive terminal, which is superposed on their random velocity. Under such conditions, the net flow of electrons across a cross-section does not remain zero. So one has an electric current flowing across the cross-section. The amount of charge passing through a cross-section of a conductor per unit time is measure of electric current and is called the ampere. Ampere if the net of the charge flowing across a cross-section of a conductor is 1 coulomb per second, then the electric current passing is called 1 ampere. If the charge passing in time t second is q coulomb, then the electric current is I ampere is equal to q coulomb upon t second. Resistance. We refer to the term random collisions between the drifting electrons and the ions located at lattice points. Actually, the ions are not stationary but execute an oscillatory motion about their main positions, the energy of which increases with the increase in the temperature of the conductor. Electrons drifting between the ions have to move through the randomly varying electric fields due to these oscillations and hence are frequently deflected from their paths. This factor is a major contributor to the property called electrical resistance of a conductor. Other factors that contribute to the resistance are the impurities in the conductor and its constitutional and mechanical defects.